Well, I know we have a lot of very busy people here wanting to hear about electrification. So let's go ahead and kick this thing off. My name is Jennifer Green. I just wanted to let everyone know that as of now, we're going to be recording this workshop. So just a heads up, this will be made available to you at the end of the workshop, but any comments that you make will be recorded. So good afternoon, and thank you so much again for joining us today for a discussion of electrification, specifically about heat pump water heaters and their applications in the home. My name is Jennifer Green, and I'm a manager of customer programs at MCE. MCE's mission is to address climate change by reducing energy-related greenhouse gas emissions with renewable energy and energy efficiency at cost-competitive rates, while offering economic and workforce benefits and creating more equitable communities. MCE is proud to present this workshop as part of our efforts to provide training to local energy workforce participants and opportunities for job seekers looking for well-paid, long-term, meaningful employment in the energy industry. This is really important work. We want to make and match great contractors with qualified, vetted, and interested job seekers. If you're a contractor working on home upgrades like HVAC, electrical, plumbing, insulation, or other energy efficiency or home performance projects, and you want to meet and work with vetted, job-ready candidates at no cost to you, we'd like to pay for one of our job-ready candidates to work with you for 160 hours to see just how good of a fit you can have with them. If you're interested, please call or email us after this workshop to talk about how to get on the list. And at the very last part, the very last slide, we'll have some contact information for you. Today's topic again is heat pump water heaters though. I really hope you benefit from this workshop and that you'll consider heat pump water heaters in your projects going forward if you're not already doing so. Electrification is the present, not even the future anymore. So let's build the space in the energy industry. And thanks again in advance for your thoughtful participation in this workshop. Let's get started, and I'll turn it over to you, Stephen.
Great, thanks, Jennifer. Welcome everybody to our second workshop in our electrification series. Today, we're going to be talking about heat pump water heating. Just a few sort of logistical things first. If you have any questions, feel free to type them in the Q&A section of the Zoom meeting. A number of my wonderful colleagues are hanging out there and will be able to answer any questions that might come up. We'll likely have some time for Q&A at the end as well. So if you have any questions, throw them in the chat box and we'll try to get them answered for you on the fly, or we can do that at the end as well. So today we are going to cover, just for starters, what is a heat pump? We're going to learn about why they're great. We'll talk about what some of the best practices for heat pump hot water heating are. We'll think about some of the considerations when putting heat pump water heaters in retrofit scenarios. And then we'll look at a few new and retrofit examples and some of the opportunities that they bring. So Jennifer talked a little bit about the workforce education and training program that this workshop is under. Ultimately, the program provides coordination with training providers to deliver a high-performance building training module to students. So these are students already in a trades training program, and the WENT Workforce Education and Training Program provides a training module supplemental to their existing curriculum with a focus on building science and high-performance building. It also provides job placement assistance to that trainee through a 160-hour paid traineeship, and then also high-performance building workshops, which we're doing one of them right now. One of the other components is also available field mentoring for interested contractors. So if you're new to electrification or want to learn more or have questions, part of this program is, helping you guys improve your business and your best practices. Like Jennifer said, there's links at the end, but the program website is mcecleanenergy.org/contractors, and there's more information about the program and how to sign up and get more information there. So why are we all crazy about heat pump water heaters? Well, let's start with a little bit of table setting here in California. So State Assembly Bill 32 collectively committed us to reducing CO2 levels to 1990 levels by 2020, which we've done and exceeded. So a round of applause for everyone. This was followed up by an executive order from the governor, Executive Order S305, which mandates a reduction of 80% below 1990 levels by 2050. That is a big number, and it's going to take a lot of work to get there. It's worth noting that while the modeled scenarios in that table do not generally simulate policies that might be put into place after 2030, it does account for emissions through 2050. So while it looks to be off target, there are still plenty of opportunities to make up that ground, but we do need to act quickly and decisively. How are we going to get there? Well, to answer that, it's important to understand where our emissions come from. So buildings are the second largest source of greenhouse gases at 26%. That's electricity and on-site emissions, with transportation as the leading source at 37% and industrial processes coming in third at around 23%. In buildings, most of those emissions come from gas, water heating, and space heating. So models don't generally account for this, but if you were to include methane leakage from gas pipelines like the huge one in Aliso Canyon, that would actually bring gas into those buildings. That greenhouse gas emissions number would be probably close to twice that. So this chart shows us where we use gas in residential buildings and is more or less the starting point for where and what end uses we need to target. So looking at this chart, for everyone not spending their pandemic working on gas-fired forges or pottery kilns in their backyard, water heating is by far and away the biggest gas-consuming end use and is generally the most energy-intensive process taking place under your roof. It takes a lot of energy to heat water. As it turns out, though, heat pumps can meet all of the end uses shown here, with the exception of cooking, although we do have induction ranges for that. So what is so great about heat pumps then? Well, they're hyper efficient. They're 4 to 5 times as efficient as equivalent gas products. They enable zero emission buildings via carbon-free renewable energy. We can utilize on-site solar, and they can act as a thermal battery. They improve air quality because we have no localized emissions. Improve safety in buildings. We have no gas lines in buildings that might explode or leak. And they can result in considerable operational cost savings from their high efficiency and their ability to interplay with renewables. So the next obvious question is, how do heat pumps work? Well, we can look at this excerpt from an MIT researcher for an explanation, but I think for the purpose of this discussion, it's simpler just to say heat pumps move heat from one place to another using a refrigerant, just like an air conditioner or refrigerator. We're just pumping heat from one space to another. So the way this actually works is through the magic of thermodynamics and the refrigerant cycle. In essence, you have two sides to your system. You have a hot, high pressure side and a cold, low pressure side. Thinking back to Mr. Fabini's high school physics class, remember that when you increase the pressure on something by compressing it, it heats up. So for example, if you squish something in your hands, it gets warmer, right? And conversely, when you decrease the pressure, it cools. So one of the physical laws of the universe is that we always move from high concentrations to low concentrations. In other words, we move from hot to cold. So if we put a hot object into a space that is relatively cooler, that hot object will move heat to the cooler space until we reach an equilibrium. The same is true of a cold object in a warmer space. That cold object will absorb heat from the space until they are again at equilibrium. It's through this method that a refrigerant can pick up heat from a space and move it or pump it to another space. So here are some examples of that in action. The refrigerator is a perfect one. We want the inside of the refrigerator to be cold, right? So by circulating a refrigerant colder than the interior of the refrigerator, we can pick up the heat that's actually inside the refrigerator and move it, thereby cooling the inside. That's why the coil on the back of the refrigerator is hot. That's all of the heat energy that we picked up from inside of the refrigerator being moved elsewhere. Water and space heating are a little bit different in that you want to bring heat into the space rather than remove it. But the same principle applies here, just in the opposite direction. So if the refrigerant being circulated is hotter than the water in the tank, well, then the water in the tank will absorb that heat and warm up. And it's then why, instead of having a warm coil, like on the back of a fridge, we end up with cold air. Same process, just backwards. So let's talk about some best practices around heat pump water heating. Firstly, it's important to understand the different configurations and form factors that these systems manifest in, and we can generally group them into 3 different categories. We have individual systems with 1 heat pump water heater per unit, so that's like a single family home or an individual apartment. We have central systems where we have 1 or more heat pump water heaters serving the whole building, and it utilizes recirculation pumps to ensure consistent hot water delivery. And then finally, we have clustered systems where a single heat pump hot water heater might be serving a few units, but generally with no recirculation. Within the individual category, we have both split and combined units. Split systems separate the compressor from the storage tank, while combined systems look and operate more like a traditional gas tanked water heater with the compressor on top of the storage tank, all combined into one package, but they ultimately both do the same thing. So here is a picture of a combined system installed into an exterior closet. So this is 1 water heater serving 1 apartment building. Same type of water heater, only in an interior closet. So you'll note that in these pictures, there is ducting leading out of the systems. This is because, as I mentioned previously, cold air is a byproduct of heating the water. And in an enclosed space, like a water heater closet, that cold air needs a way to exit. Otherwise, the system efficiency can dramatically be reduced or not work at all. So we'll look at some of the venting requirements a little bit later, but ultimately, you'll want to refer back to the manufacturer specifications for information on ducting and fresh air exchange requirements. Ducting can typically be eliminated by placing a unit in a large enough space, like in a single family home, maybe in your garage, or by utilizing a fully louvered door that allows ample air exchange. There we go. So when we're talking about individual water heaters, there are a few things you might want to think about. So we typically use these in single family dwellings or in apartments where each resident has their own water heater. Some of the nuances around multifamily applications of single individual water heaters are that they're typically located in closets, not in a garage, because people in apartments don't typically have garages. We have to, generally duct because there's oftentimes volume space challenges for the air exchange. And generally there's going to be more limited electrical panel capacity in breaker spaces. These are ultimately electrical devices, so we need to be able to power them. There can be increased complexity for dedicated circuit runs that may or may not already exist at that closet. And because a lot of these are connected to the grid, utilizing the storage tank as a demand response piece, there can be some complications with tenant turnover and the associated need for connectivity. Also, a lot of apartments have fewer water fixtures than like a single family home might, but they'll have higher occupancy density relative to a single family home. So sizing them can be a little bit, you have to think about it a little more. Really, the electrical issue should only be a challenge in retrofit. This is a non-issue for new construction where we're designing these things from the start to be able to accommodate these types of systems. So when we move on to central or commercial equipment, this is kind of where it gets a little more interesting. There are a wide variety of products available for larger centralized hot water systems. They operate with the same principles, but have higher compressor capacities and are able to more adequately heat larger volumes of water more rapidly. So these systems generally will require a much larger volume of stored water to meet the higher demand for the building. Most of these types of systems will be split, like we see here on the left. where the storage tank is separate from the compressor, similar to how like a boiler and a tank system would work. There are some combined ones, albeit less common, where everything is combined into a box, but they do exist. And there are a lot of different ways that these systems can be sliced and diced, and so we'll show a few different configurations right now. So this is a system manufactured by Colmac using one compressor and 240 gallons of storage. This is the compressor over here, and these are the storage tanks. This is another system manufactured by Colmac, but using two smaller compressors and a similar volume of hot water storage. The advantage here is that the two compressors can act as stages with only one operating during periods of low demand and minimal recovery needs, or both turning on with high demand. You can also operate them as a duty cycle, increasing redundancy and lengthening the expected useful life of the equipment. So this is the same size heat pump as the last installation, but with less storage and only a single compressor. And the reason here is that this is just a much smaller property. The point there being is that these systems are pretty scalable. You can, you have heat pump water heaters that can serve single units all the way up to, hundreds of units. Colmac is, of course, not the only manufacturer in town. This is a system manufactured by Sandon, where multiple smaller compressors are sort of ganged together, resulting in a really high degree of modularity and variable capacity. There are definitely some complexities with this approach, but when it's well executed, it has a lot of merit. And this is a similarly configured system by Sandon, but trading off less compressors for more hot water storage. This is serving 66 units of low-income family housing. And then really finally, just to give a sense of like the scale and size of building where this is possible, this is a UCSF dorm building housing 333 student units and 4 very large compressors made by, or heat pumps made by Nile. Make this all work, this project has a ton of hot water storage. I believe it's 3,000 gallon tanks, so a total of 3,000 gallons of hot water storage. But it ultimately translates to a significant amount of hot water capacity, and is able to serve over 333 beds. So how do we choose the configuration? There are some considerations that might make us choose for one over the other. The individual approach, if you have a more spread out development with larger units and you have space and ample air exchange, you might go with an individual one. Or if you have individually metered buildings or like owner occupied condos where the resident needs a feedback mechanism for their usage, this is a great example. It's nice because there's a ton of equipment selection, pretty easy to find. And there are no Title 24 hot water requirements, PD or thermal, so you don't get dinged for not having thermal. And then you can save a lot on cost of recirculation piping, but ultimately the trade-off that you have there is that you have more pieces of equipment in each unit, right? So now you have one water heater for each unit. Central systems are great for very dense developments with maybe smaller units and tight sites. So like they're good for high-rise or mid-rise buildings. They're good for master metered buildings where each tenant is not receiving their own bill. Really the owners focus on their own operational cost savings. The flip side is that there's a little bit less, there's more limited equipment selection, and these central systems are subject to Title 24 solar hot water requirements. The flip side is that there's less hot water equipment overall, and so they're easier to access and maintain. You really only have, one plant potentially, or depending on how your property is laid out, multiple plants for different buildings, but one plant per chunk. And then we have kind of like clustered. These are sort of unique. We don't see them very often. I am working on a project where we have one heat pump water heater serving 4 units, and there's no recirculation piping. So for properties like that, where it's like a small garden style property with a small number of units in each building that you might be able to address with a single heat pump water heater, that's kind of a good way to approach. You do still need to locate the equipment in each building or cluster. So the next kind of thing that we got to think about is the storage versus recovery conversation. So for a gas-based system, Really, typically, we're going to have a relatively small storage capacity, sometimes zero if you have a tankless system, and our recovery is going to be really fast. You can think about gas systems as utilizing a flamethrower to heat water, whereas with a heat pump, you have a very large storage capacity, and it's more akin to a simmer. So the recovery time is going to be longer. But Aesop's fables taught us that slow and steady wins the race, and I think that's pretty apt here. So large storage tanks, small heat pumps. Really, the advantages are that it reduces the overall hot water system cost. Storage tanks are a lot cheaper than heat pumps. It reduces the building's electrical service requirements, including wiring, panels, service, and it reduces owner exposure to high peak demand charges. We can reduce our heat pump equipment short cycling by making sure that there's ample storage, and it improves resiliency in the event of a power outage. Really, it's like a thermal battery. If you have at that UCSF building, you have 3,000 gallons of hot water storage, right? Like that can take you a long ways without any power. The kind of downside is that you do need to place the tanks and the water's heavy. So, if you are in a retrofit scenario and maybe your plant's on the roof, you got to think about can the roof support all that weight? Again, less of an issue in a new construction scenario where we're designing from the ground up around these systems. So here are some common configurations for gas-based systems. They're ultimately different from each other, but these are even more different from how we would design a heat pump system. So at the top, we have a gas tankless system with a lot of recovery capacity and no storage. And then down here, we have a gas tank system with a little bit of storage and less recovery, but we're trading off storage for recovery. So for a heat pump, you would want something more like this. We'll utilize a lot more storage and a lot less recovery. So ultimately, your recovery period is generally going to be longer, but the reason for this is if you took a similar sizing approach of the gas tankless system, you would have a kilowatt demand of 47 kilowatts. With a little bit of storage, in this case 200 gallons, you could get it down to 31 kilowatts. Now, if you have a ton of storage, you can knock it all the way down to 11 kilowatts. So this has positive knock-on effects for other things like electrical service size, demand charges that you would be subject to because those are a thing, as well as other things down the line. So really, this shows that sizing with a similar approach to gas will result in a huge electrical draw. And because demand charges exist, we quickly reach a point where these systems do not make any financial sense. So the solution then is to trade off a higher heating capacity for more storage to be able to achieve a desirable outcome. At the end of the day, we size these systems in a very different way from how we would approach a gas system. The work that AEA does is primarily related to multifamily buildings. So that's the typical lens that we look at these systems through. But if you're attempting to do something different, like, I don't know, a gym or something else, you'd ultimately need to understand the demand profile for whatever your application is and adjust your storage and capacity accordingly. So piping is a big thing. There are a lot of different options and there are a lot of trade-offs for each option. You're going to ultimately want to weigh simplicity versus performance for your project. The most efficient central heat pump water heating system might be more complex and might have higher first cost, but might likely have lower lifetime operational costs. For these reasons, it's really important to have an engaged engineer and a manufacturer's rep, especially if you're just starting out doing this kind of work. So the first way that you could pipe one of these systems is really the most similar to gas piping. You put a heat pump where the boiler was. You pull the water out of the tank and you heat it up and you put it back into the tank. If you pull 100 degree water from the tank and heat it up for a while to 110, put it back into the tank and then do that over again and heat it to 120, it's ultimately heating the water up over multiple passes through the heat pump. So we call these multi-pass systems. The tank will be heated up slowly over time, but the heat pump will only heat the water up a small amount each time. This is not necessarily the best approach, but there are products that can operate this way. Like I said, it's oftentimes important to weigh simplicity against performance. Really, though, the most prevalent systems for central heat pump water heaters are single pass systems. So single pass systems are pulling very cold water from the bottom of the tank where the cold water makeup comes in down here. And then it's heating that water all the way up to the set point in a single pass. So it's only going through the heat pump one time. Generally, that's going to be like 150 or 160. We want to heat the water up really as high as we can because that actually allows us to mix down later and nominally increase the hot water that we're able to deliver. So if we were just storing at the temperature that we wanted to deliver, we would have what's in the tank. But by storing at a higher temperature, we can mix down, thereby increasing the volume of water that we're able to deliver while it's hot. So you want to put that very hot water into the top of the tank here. By doing this, we are effectively heating the tank from the top down. Consequently, this is also where the hot water goes out to the building. So by doing it this way, we are effectively ensuring that we are always delivering the hottest water possible available to the building. So the likelihood that the water that we're delivering isn't warm enough to the building is minimalized. The reality is that these are central systems, though, so they likely will have recirc piping. So where does that recirc connect? If we were to take the traditional gas-based approach to recirc, we would connect it to the cold water makeup. This is what we do with gas water heating systems. So why not do it with heat pump water heaters? Well, for one, with a single pass heat pump, it's going to operate most efficiently when the water coming into it is as cold as possible. Generally speaking, the larger the lift from incoming water temperature to outgoing water temperature, the more efficiently the system's going to operate. So if we pipe the recirc into the cold water makeup, this might increase the water temperature going into the tank and warm up the tank. So we probably don't want to do that, actually. So, well, maybe we can pull that recirc water into the middle of the tank, away from where the heat pump is pulling water, right? So the heat pump's pulling water from the bottom. So if we put the recirc in the middle where it's not pulling from, would that work? Would that be better? Well, one potential downside of this is that this can then destratify our tank and lead to lower delivered water temperatures. Essentially, if you have a relatively high volume of recirc water coming in, the turbulence can end up mixing up this water in here, effectively, making the whole thing warm. Really, we want the tank to be stratified. We want really hot water at the top, and we want cold water at the bottom. So we're delivering really hot water, and we're putting cold water into the heat pump. But if we start mixing it up with this, high volume of water coming into the tank, this is going to go from hot and cold to just one warm tank, and that's not good. So what if we separate it entirely? So what most people are doing designing these systems now from scratch, especially in new construction, is separating the storage tank, or separating the recirc entirely from the main storage tank. So you now have your primary storage tank on the left here, and a single pass. You have your primary storage tank on the left, and the single pass heat pump water heater only sees the coldest water possible coming in from the street and this tank, and is thus able to operate at maximum efficiency the whole time. Then you have what we're calling our recirc tank here, where our recirc piping comes into the tank. This is piped in parallel with the main tank. You can do this with a residential heat pump water heater or with an electric resistance. So this system, oops, getting mixed up here. Is that system going to operate super efficiently? Well, no, because it's always going to see warm water, but it's ultimately only handling the recirc load, so it's not the end of the world. What this does is it allows your recirc heater to operate at mid efficiency, but allows your main water heater to operate at maximal efficiency. The reality is slightly more complicated because we're actually going to have a mixing valve in the system. So it tends to look more like this, but the overall dynamics are more or less the same. When people talk about heat pump water heater configurations, they typically say whether the system is a single pass or multi-pass system. So in this case, we have a single pass system with a recirc tank, sometimes called parallel recirc because the recirc tank is in parallel with the main system, meaning both tanks are feeding the mixing valve together. The advantage of this approach is that it's very efficient, especially with CO2-based single-pass water heaters and a multi-pass heat pump recirc tank. The disadvantage is that this is complicated to design and install. You've got more different components. You have water heaters now, which translates to higher install and maintenance costs, but it can be done and it's relatively common. Another way to do this is what is kind of becoming the de facto standard, and it's utilizing what's called a swing tank. So look at where the water heater coming out of the stratified storage tank goes. Here, we're going into the swing tank and then going into the mixing valve. Here, we're going into the mixing valve, and the recirc tank is also going to the mixing valve in parallel, right? So you guys see the difference? Coming from our main storage tank here, we're going into the swing tank, and here, we're coming into the mixing valve. So in the previous version, water goes straight into the mixing valve, and here it goes into the bottom of what's now called our swing tank. And now our swing tank is in series, right? So the water isn't going directly from our main storage tank to the mixing valve. It's going from the main storage tank to our swing tank and then into the mixing valve. No longer in parallel, but piped in series. This has some advantages. One is that if you have regular enough demand from the building, from people doing laundry, opening faucets, taking showers, whatever, that's going to pull cold water makeup into your system down here, which is then ultimately going to move hot water from your main storage tank into this swing tank. And so your superheated water from the main tank over here is going to ultimately charge your swing tank. This, in theory, lets us meet all of our building load and our recirc load with the one single pass heat pump water heater. Now, if we don't have any demand for a while, we have no water coming to this tank, we have no water then pushing into the swing tank, this swing tank is going to sit for a while, and it's ultimately going to kind of cool down as the recirc load comes in here and starts to dilute it. So this swing tank ultimately needs to have some heating capacity. Usually we do this with an electric resistance element. You could do it with a multi-pass heat pump for maximum efficiency, but it again adds like a little bit of complexity and cost. Typically a resistance heater is used for the swing tank, but there's nothing fundamentally stopping you from utilizing a heat pump here. Because the whole building load is ultimately being met from this swing tank, all the fittings do need to be sized for full flow because the whole building's flow is coming out of the swing tank rather than from here. So piping layouts are all good and fine, but like, wouldn't it be nice if we didn't have to do all this stuff? Like if we could just bring the recirc back to the tank like we used to. So how much simpler would that be? Like a lot, right? So maybe if we're able to keep our recirculation flow really low by controlling our recirculation pump with a variable speed pump, and we also have like a really big storage tank for our main tank, maybe with a very low flow rate of cold water going into the bottom of that stratified tank, it would be okay. So to be clear, this is not a standard practice right now, but we're studying it on a number of grant-funded research projects, whether or not this can work. So the idea is that like if we have a big enough, hot enough tank with a small enough, cold enough recirc return, this could work, right? So we know that if you have a high flow rate of warm recirc water in a small storage tank, this is like a really terrible idea, and you definitely don't want to do this. But you got to think that there's a tipping point somewhere where this would in fact work. We're kind of trying to figure out where that tipping point would be, because it would really simplify things and it would be really nice if this worked. We don't really know where the point is yet, so we're not recommending that people go out and do this, but I mean, it really definitely seems like it's theoretically possible. You know, the advantages here would be that it's dead simple and it's like really similar to a traditional boilerplate design. There's fewer components to maintain. Like you only have one heat pump. You don't need the swing tank or recirc tank. And it's like really widely applicable for retrofit applications too. The downside here is that you probably have a slightly lower system COP, but not really if you compare it to a recirc heater. And I think the semi-reduced efficiency would be really outweighed by the simplicity of the system. So really the idea being that the minimal recirc flow would not negatively impact the temperature of the stratified storage tank, such that the simplicity of the design outweighs that negative efficiency impact. All right, so what about heat pump water heaters and solar, right? So do we just do solar thermal like we always do? So solar thermal preheats incoming water, but if we remember that heat pump water heaters are most efficient with cold incoming water, that kind of presents a problem, right? Well, but also isn't solar thermal better at capturing solar energy than PV? Well, yeah, solar thermal panels are more efficient on a square footage basis than a PV panel is. But if we go back to the beginning and we think about the magic of the refrigerant cycle, this solar thermal panel is going to deliver, call it 3 BTUs to the hot water tank. So this solar panel is going to pick up maybe 1 BTU worth of energy, but using our heat pump and the magic of thermodynamics, that BTU actually from the PV panel can produce 3 to 5 BTUs of heating capacity. So it's at a minimum as good, if not better, than a solar thermal system in that regard. If we think about solar PV versus solar thermal, on the PV side, we have no moving parts. We have a system that can potentially offsite 100% of our water heating load for buildings that have enough, usable, roof area or carport or whatever. As long as we have enough space for all the panels, we can conceivably offset 100% of the load. Only simplifies building, like we only have one system that we have to install now instead of a solar thermal and a PV system. And it doesn't impact heat pump water heating design, right? Like we're not introducing now a warmer flow of water into a system that already doesn't want to see it. It should be monitored for performance, same as any other renewable system. The kind of downside is that you do receive limited energy code compliance credit for PV. On the solar thermal side, we have moving parts. We're moving around fluid, so we got pumps and things that are going to break potentially. The spoiler, they always break. I don't know how many buildings I've been on where the solar thermal system is broken or like barely functional. And at most, it's really only probably going to offset like maybe 60 or 70% of the hot water load for a building. Like it's not always hot outside, right? They work, but there are days where it's cloudy. You're never going to be able to hit 100% with a solar thermal system. Having the two systems together, PV and thermal, complicates things. And like we're talking about, because it preheats the water, the integration of a solar thermal system with the heat pump water heating design is like overly complicated. It's really generally not advised for that reason. The one positive side is that you get significant energy code compliance for solar thermal. So, there are some benefits in that regard, but it's, kind of a specific use case. So really all that is to say that solar PV is the best approach for heat pump water heating systems for, the variety of reasons that we just talked about. One of the other cool things about heat pump water heaters and solar PV is the interplay with storage. So, right, like storage tanks are pretty cheap relative to, say, a big lithium-ion battery. So if we take that storage tank and we're able to, store our PV energy in that tank via heating that water, we can add a brain to that. If we size it adequately, we can now load shift and optimize for time of use and energy consumption and all sorts of demand response capabilities, and there's a lot of positive synergy that we can achieve there. All right, so let's think about some considerations in retrofit scenarios. Heat pump water heating is not that challenging to implement in a new construction scenario where we're designing from the ground up for that type of system. When we're trying to retrofit an existing gas system into an electric heat pump water heating system, there's some things you need to think about. So one of the first ones is existing recirculation systems and the presence of crossover. So what crossover is essentially usually cold water, not always cold water, but cold water enters the hot water system through failed plumbing cartridges, right? You have a hot line and a cold line, and those hot and cold lines, they communicate with each other occasionally, right? Like at your shower head or at a mixing valve or at your sink if it only has a single handle. And what keeps those things from moving across to each other is a cartridge. And if that cartridge fails, whichever of those two lines is higher pressure is going to win over, right? And that higher pressure water is going to start pushing into the lower pressure side, right? Remember, we go from high concentrations to low concentrations, high pressure to low pressure. And so what ends up happening is our cold water becomes lukewarm, and that ultimately reduces our heat pump water heater efficiency. So just for example, a high-rise retrofit project I'm working on in Southern California, over 40% of the cold water in the building is entering the plumbing system via crossover. So like that's a lot, right? And so like just kind of looking at this, you know, we have crossover flow and imbalanced recirculation that makes our recirc pump maybe go from our controlled method to our constant operation, because now the recirc pump is seeing you know, funny temperature water. That makes our heat pump tanks destratify. Now that ultimately lowers the operating efficiency of that system. It's a big deal. Location to mitigate crossover, right? So we talked about you know, showers and other single handle water fixtures. When the cartridges in those fixtures fail, they you know, they allow the higher pressure water to bleed over. It's more often than not the cold water bleeding into the hot line, because that has street pressure. Sometimes it's the hot water bleeding into the cold line, but mostly it's cold water. Mixing valves are another really common location, right? Like you remember in those piping diagrams, we have mixing valves because we're storing really hot water. We need to mix it down to a more reasonable temperature so that we don't scald people. That's another location where that hot and cold line, they interplay. And you know, if that mixing valve fails, whichever, you know, water is higher pressure is gonna, you know, win out, right? And then, you know, we have unbalanced distribution. So in like, you know, buildings that have stacks, maybe the stack furthest away is really only seeing like a little bit of flow, and the one really close to the pump is seeing a lot of flow. So without balancing, certain wings in the building or stacks in the building can experience, you know, higher or lower flow rates than other parts of the building. So how do we fix these things? Well, we can replace all the failed shower and faucet cartridges. It's kind of time consuming to try to isolate these things. So depending on what your rehab scope might be, you might just say replace all the shower cartridges and any single handled cartridges. You know, we can install check valves on the hot and cold line before the fixture to account for any future failures. So a check valve will only let the water move in one direction. So even if there's a failure, that high pressure water is trying to push into the low pressure line, that check valve is going to say, nope, water can only move in one direction here, right? Mixing valve, same thing. You know, if we just replace the mixing valve with one that's not broken, those two, you know, hot and cold lines are not going to communicate anymore. And then finally, thermostatic balancing valves and variable speed recirculation pumps. So if we have a thermostatic balancing valve, that lets our variable speed recirculation pump maybe dial the flow rate down really low because everything's balanced and we actually don't need a ton of flow to, you know, meet our needs, which gets back to that potentially ideal scenario of, well, can we deliver just like a really small volume of recirc water and then really simplify our overall, you know, plant design? Possibly. This is some data logging that we did on a building that had really significant crossover issues. So here on the left side of the chart, you can see the supply and the return temp. The blue up here is the supply temp, and the orange down here is the return temp. And you can see there's like a really large delta between the water that's going out and the water that's coming back in. This line here represents where we did the crossover mitigation work. And you can see after that line, the delta between the supply and the return temp, the temperature going out and the temperature coming back is like a lot smaller, right? So it's pretty obvious where it exists, and then it's pretty obvious once you fix it if you do data logging. Something else we got to think about on existing buildings is like electrical capacity, right? So like, do we have sufficient service capacity? You know, my house, I have like a 60 amp, you know, panel on my house. It's like completely full. I'm in the process of upgrading it, but I actually couldn't do this in my house if I wanted to right now. So equipment from the 70s or older might trigger service or panel upgrades, which is what I'm going through right now, actually, so that I can, you know, enable this kind of work. A 100 amp panel is usually going to be okay for some amount of added load. And where capacity is at a premium, there are 15 or systems that require only a 15 amp breaker, like that stand-in systems that we showed back in the beginning. Those only require a 15 amp breaker. I mean, obviously that's only going to be for like a single family or individual style, you know, heat pump water heater. But there are systems that don't require a ton of electrical capacity. Beyond the like the capacity part, like, can you deliver enough power? Do you have enough space? Like, in my house, I don't have enough capacity, but also I don't have any space either. So even if I had the capacity, I don't have any place to land a breaker. And that's pretty common in older buildings. Okay, so you got space. You have access to run wiring to the new water heater. Like, your old water heater may or may not have needed electricity to work, right? You light the pilot light and that's it. So you might need to run new wiring. It's usually pretty easy in single family homes where you have attics or crawl spaces, but like, what about multi-story apartment buildings where you might not have access to all those places? So just stuff to think about as you're kind of working through your projects. These are things that are maybe going to come up. Beyond that, we need to locate the water heater, right? So we talked about, clearance and space requirements before for venting. So different requirements for different brands. But in a lot of cases, the water heater closets are really small. They're sized for like, an old 40-gallon water heater that has no venting requirements other than that you need the combustion gases need to be able to leave. So sufficient room volume is required when not vented. So like if you have a garage, that's probably a good place to put it. But if you have a small closet, you need to figure out some sort of venting solution. Here are some space requirements for an individual heat pump water heater made by state, right? We have a number of different configurations. On the left-hand side, we have an enclosed room called a garage. If you have 700 cubic feet in that garage, you're golden. You don't need to vent or do anything, okay? An example of that space is an 8 by 8, basically in a 10-foot tall ceiling. Boom, good. You can just dump it in the room, call it a day. It's going to put some cold air into the room, but ultimately you have enough space there that exchange can happen without any issues. A little more challenging when you move it into a closet, right? So here, if you have a single louver in your door, which is a fairly common, like old, water heater closet kind of thing, just have, one single vent for combustion ventilation air. You need 300 cubic feet. That's kind of a lot, actually, isn't it? A 5 by 6 by 10. Like, whose water heater closet is that big? That's like a San Francisco bedroom. Well, if we have, 2 louvers in the door, so now we have more effective, air exchange happening. We have 2 louvers. The space requirement moves down to 120 cubic feet. 3 by 4 by 10. That seems more reasonable for a water heater closet, right? 3 by 4, 10 foot. That's still probably pretty taller than maybe your water heater closet is, though, actually. So what do we do then? Well, we can then duct our air in or out. So if we, take a ducted approach, we actually don't have any minimum space requirements. Like if you can physically fit the thing in that closet and you can duct the air out, you can put it in as small of a space as you want. But then you have to duct it. And you have to figure out how you're going to run your duct. Where's it going to go? Like all those kind of things. So just, stuff to think about. There's a lot of different ways that you can do this. And each of those, has considerations you need to think about. We have condensate drain. So on your old water heater, you probably didn't have a condensate drain unless you have a condensing water heater that has condensate. But on the old water heater that I have in my basement, there's no condensate drain. So this equipment does require a condensate drain. It can either drain by gravity or with a condensate pump. The preference is typically gravity because with the pump, you're introducing another mechanical part that potentially can fail at some point. Different jurisdictions treat condensate differently. It's, typically not corrosive. So usually the following will work. Can put it into an exterior planter. The washing machine drain can share with the air conditioner drain, can connect right to the sewer. It's not like a condensing water heater where the condensate is acidic and you need to bump the pH up, through like limestone chips or something like that. It's really just water. Let's do like a little locating exercise. This is a 2-story project with interior water heater closets. So let's think about how we're going to route this and like what we need to think about. So these yellow circles here, this is where the existing water heater closet is, right? So what do we need to think about when we're going to replace these with heat pump water heaters? So what are we going to do for venting? Well, we could either maybe do a soffit and put it out the wall. We could maybe go up through the ceiling, but who knows what, is there another unit above this? What's the roof look like? How are we going to get electrical here? There wasn't electrical here before, so we need to think about how we're going to bring electrical to this space. Okay, so this is an interior water heater. What are we going to do for a condensate drain? Like, how are we going to put that outside somewhere? It has to go somewhere. Well, we're on the back side of the bathroom. Maybe you can tie it into the bathroom, drain. And then again, clearance, like, can you fit it into the closet that exists, or are you going to have to modify the closet? These are all things you need to think about. None of them is like a bridge too far, like an unovercomable hurdle, but there are things that you're going to need to think about potentially. Thinking about some of the other challenges. So, we talked about the storage volume, so space or structural can be a constraint for retrofits in some buildings. Like water's heavy, right? Larger volumes of stored water and locations for the heat pump. You got to think about that stuff. Where are you going to put it? Can you keep it on your roof? Do you have enough space? Do you need to build a new pad? Noise can potentially be an issue. You have a compressor now, and if you hang it on the outside of the building, which is super common, plenty, reasonable way to do it, maybe that compressor is now like facing into somebody's window and like they're not going to be too happy. So you got to think about where the compressor is going to go and like what the noise implications of that might be. One of the other challenges is just a general lack of product knowledge amongst like building owners and the general public, which kind of translates into maybe a hesitancy to move forward. Like conceptually, a regular water heater is like really simple, right? Like it's easy to wrap your head around. You have a gas, you set the gas on fire, it makes things hot, and then you have hot water. It's like not rocket science. Heat pumps, like you got the word thermodynamics in there. There's like other stuff going on. It's like a little bit harder to wrap your head around. People just aren't as comfortable with it as a technology. So it can translate into like a little bit more hesitancy to move forward. Since you're moving from a gas end use to an electric end use, you have to make sure that your utility rate structure is correct. Otherwise, you might get actually, instead of saving money, it might cost you money. I'll show you an example of how that manifests a little bit later. And then, similar to general building owner knowledge, lack of contractor knowledge is like that's an important one. People tend to price things based on how comfortable they are with stuff, right? So if I'm a contractor and I'm bidding something, if I know that I don't know how to do this and I'm going to have to factor in some like figure it out time, the price that I give is probably going to end up being higher than, it might be otherwise for something that I'm totally comfortable with, right? And then just because these are relatively new products, well, not new products, but the material cost is generally going to be a little bit higher than a comparable gas product. So all that said, we have ways to kind of approach that. There's lots of money available out there to help move the needle, transform the market and bring costs to a competitive level. So MCE has a water heater incentive. The program offers up to $1,000 paid directly to licensed contractors for replacing their customers' natural gas or propane water heaters with heat pump water heaters. A similar program is available through BayREN for other utility service territories. Then beyond that, MCE has electrification programs up the wazoo. We have the Low-Income Families and Tenants program, which is for low-income buildings. We have the Multifamily Energy Savings Program, which is, covers a host of multifamily building improvements. We got programs for battery storage. Advanced Energy Rebuild Napa has similar programs. And then, like I said, we have the heat pump water heater program for MCE. And then what if you're not in MCE territory? Well, I'm telling you, there's money out there to do this stuff and to make it cost competitive. City of Palo Alto has their own program. Silicon Valley Power Company has their own program. East Bay Energy Watch has a program. BayREN has a program. The state of California has a program called the Low Income Weatherization Program, which gives buku bucks for multifamily buildings that want to do fuel switching. The money's out there to make this stuff cost competitive, and we're really trying to drive the market in this direction. So the money piece is important. Okay, so let's look at a few examples of heat pump water heating and kind of take a look at what the actual impact of making these changes are. So this is a fancy new construction building. This is Edwina Benner Plaza. It's a new construction building in Sunnyvale. It's an all-electric affordable housing development. So this project has won like a ton of awards, thanks in large part to its all-electric building approach, and it prominently features a central heat pump water heating plant. The project team was able to show that there were no significant differences in the construction cost of building this all-electric property versus a traditional property. And then on top of that, they were actually able to achieve cost savings due to the availability of grants and additional funding for all-electric construction projects. Like if we go back to here, we say, oh man, there's all this tons of money. Well, can we use it? Well, yeah, actually. So if we have a system that's cost competitive, because we actually, with all electric building, we have no gas piping now. There's all kinds of positive cost savings from not including gas in a building. And then on top of that, there's incentives available to say like, hey, you guys should do this kind of work. So this is like this is a great project, ton of awards, all electric heat pump water heating project. So like, let's look at some retrofit projects. So this graph here shows our energy use pre-construction and then post-construction. This is a property located in Fresno. It was built in 1974. It's 93 units and about 65,000 square feet. They have a central domestic water heating plant that switched from gas to heat pumps. And then they also did a number of other things too. So they did some LED lighting, they did some domestic hot water controls, low flows, and variable speed pool pumps. So the electric savings are from other stuff, but the majority of it is from the heat pump water heater. Excuse me. The net result of that work is the realized annual energy savings of 65%. Like that's pretty significant, right? 65%, 82% gas savings. And then electricity did go up because we've switched our gas end use to electric end use. So that's to be expected. Now, let's look at the cost savings. So the issue here, so the owner's actually still realizing a cost savings of 5% year over year, but there's kind of two issues here. First is that they did not switch in a timely fashion to their all electric utility rate. So they're still paying the same utility rate that they were paying before, but they're paying on a lot more electricity use. Utility has utility rates for all electric buildings that provide a larger baseline. So I'm not sure what it would be if they had switched, and I believe they've switched already. The other kind of challenge that's not reflected here is they installed a large solar electric system, but they've had a number of issues getting PTO. Permission to operate. So once that system comes online, the cost savings are going to be, the net of a better, more appropriate rate structure, as well as having all that additional electricity usage subsidized by the new solar PV system. I'm actually really curious to see what this turns out to be after the solar system comes online and the rate structure gets changed. But as a starting point, we're already at 5% cost savings. This is another one. This is a project located in Sacramento, built in 1960. This is 36 units and about 37,000 square feet. Similarly, we had a central domestic hot water heating plant that we've switched to heat pumps. And on the left-hand side, again, we have the pre-period, and then we have our construction period over here. And this is our post, and it's like, whoa, look at that! What a drop-off, right? So here we've realized an annual energy savings of 64%. We've cut 89% of the gas usage out of the property, and only a 33% increase in electricity. So we did also some LED lighting and some domestic hot water controls, as well as low flows. So low flows are great for heat pumps because they have positive effects on, we have water savings from that, but we also have positive cost savings from reduced hot water load. So there's an incentive to do that kind of work as well. That's like a really low-hanging fruit and a good way to increase the positive impact of your heat pump water heating project. Let's look at the cost savings. This is a pretty compelling graph, right? So here we have a realized cost savings of 36%. We have 90% cost savings on our gas bill, and we do have a 25% increase in our electricity bill because our gas water heating end use is electricity. But the net of those two is an overall cost savings of 36%, which is pretty compelling. And then finally, I just kind of wanted to look at what an in-unit heat pump water heating retrofit might look like. So this is a property in McFarland, California, of Kevin Costner running movie fame, McFarland, USA. 52 units, 60,000 square feet. We had a unitary water heater, so each unit has its own water heater, and we switched those from gas to heat pump. We also had unitary HVAC, which was gas furnaces and air conditioners, and we also switched those to heat pumps. So this graph shows both savings from water heating fuel switching as well as space conditioning fuel switching. And again, this over here on the left-hand side is our pre-period. I believe this right here in the middle before the yellow line right here is our construction period. I want to say it's 3 or 4 months. And what this yellow part down here denotes is what our projected PV is going to be. So really, the difference between the top of the yellow part and the top of the line here, that's what our actual energy usage is going to be. Similarly, on the cost side, we have huge cost savings for the residents, right? So in most months, we're running a net negative on cost, or positive. The cost is zero or less than zero. And then in a few months in the wintertime, when the heat pumps are rocking and rolling because it's cold and there's less PV production, the PV is not able to cover all of the load. But in general, there's a ton of utility savings for the residents here in this in-unit scenario. So these are just kind of 3 different projects that I find to be pretty compelling that I wanted to share with you guys. And that's all we got. Thank you everybody for showing up. I really appreciate all your attention and everything. If you have any questions, you can reach us at workforcedevelopment@mcecleanenergy.org. You can reach me directly at sgribble@aea.us.org or Jennifer at jgreen@mcecleanenergy.org. Jennifer kicked off the meeting for us. And then if you'd like more information about the Workforce Education and Training Program, if you're interested in heat pump rebate, you can find information there. Or if you're a contractor that's interested in potentially receiving a trainee, we'd love to talk to you. Or if you're a contractor that's interested in field mentoring, you want to improve your business and include electrification in your scope of work, we would also love to talk to you. I'm not sure what's in the Q&A chat. Hopefully everybody got answered. We have a little bit of time left, so if folks have questions, we can stick around and do a little bit of Q&A. Happy to do that as well. But again, just wanted to thank everybody for your time and attention, and hopefully you found this to be useful.
Hey, thanks, Stephen. This is, can you hear me all right?
Yep, I got you.
So there are a couple of questions in the chat that didn't, so a bunch of people put things in the Q&A. Thanks to everybody who put questions in there. There are a couple of questions in the chat that I just wanted to call out real quick. Let's see. We've got one. How do you recommend avoiding, this is from Kim Zilker, how do you recommend avoiding crossover in the future in new construction, domestic hot water heat pump projects? Probably doing the same things that you all are doing in retrofit to keep it from happening. Can you just run back through that again?
Yeah, check valves are going to be like kind of the future-proofing piece of that, because ultimately, the cartridges are like a nominally mechanical piece that is going to fail at some point. There are different cartridges that, some of them will fail in the open position and some will fail in the closed position. And, a good approach is finding, and I think we have this list, one of my colleagues, Jack Eichison, has started to put together a list of different cartridges that will fail in a position that will not induce crossover or will induce less crossover.
These are shower cartridges.
Yeah, shower cartridges, exactly.
And then the check valve that you mentioned, where would that check valve go to sort of be the ultimate backstop against crossover?
Yeah, on the hot and cold line leading up to wherever that communication point is. So like if you have, I don't know if you can see my screen, but if you have your like your shower valve here, you have a hot and cold line coming into that, you would put your check valves on the hot and cold line coming into that shower cartridge, so that if that cartridge fails, the high pressure line is not going to be able to push into there. So when you're doing your plumbing, you just put a little check valve in each of those lines before the shower valve or whatever sink or whatever it is.
Got it.
You can also do check valves before the mixing valve too. It's like bigger piping, so it may be a little bit more money than like a 3/4 inch check valve, but that's another location that's pretty common as well.
Yeah. Okay, cool. There's another question in the chat. For single family home, how does a multi-pass heat pump function with solar thermal to preheat the water during the day with a large storage tank to hold enough heat over? Yeah, I mean, that's a very specific question about a very specific system type. You'd really have to check with the heat pump manufacturer to make sure that it's going to work well with solar thermal. Most of the heat pump and solar thermal sort of interactions that Stephen was covering were about central systems. For a single family home, the dynamics are gonna be a little bit different. I don't know, Stephen, do you have anything to add on that?
Not quite off the top of my head. I mean, I guess if you're deciding on whether or not to put a solar thermal system in, I would say you should probably do the PV system just because it's going to be simpler. But I'd be happy to talk to you about your specific problem. If you want to shoot me an email, we can kind of see if we can work through it a little bit.
There's a note from MCE that the MCE heat pump water heater contractor incentive is stackable with the Bayren Home Plus homeowner incentive. So just so people know that you can stack those two incentives, and you can get that information on MCE's website. There's a question from Caitlin. How do we move the needle to electric heat pump water heaters where electricity cost is greater than gas? Oh, the age-old assumption that electricity costs more than gas. Stephen, do you want to take this or do you want me to?
Well, so the reason why this works is because the efficiency of a heat pump water heater is considerably higher than that of a gas water heater. So on a per BTU basis, gas might be cheaper, but when you factor in the mechanical advantage of the heat pump, that's mitigated. It can be, the real answer is it's potentially challenging in a place like California where the utility costs are high. But the reality is that in most cases, the mechanical advantage of the heat pump is going to, overplay the cheaper upfront gas cost.
And if we look at sort of long-term projections for gas prices, as people move off of the gas system and away and onto electricity, the fixed costs of maintaining the gas grid are going to be shared among a smaller and smaller set of customers. So gas rates are going and are projected to continue going up considerably. Let's see, other questions in the chat.
Oh, a follow-up to that question though, if you have solar PV, you don't have to pay for the electricity. So the retail cost of electricity is a non-factor anymore, right? So then you're comparing the cost of your PV system versus the retail cost of gas, and that's a much different equation.
Yeah.
Anything else on there that hasn't gotten answered yet, Nick?
Not that I can see, no. We have a few more minutes if anybody thinks of anything or wants to put anything in the chat or in the Q&A.
Hey, Nick, it's Stephen. Do you know if this presentation can be made available, the slides made available to attendees?
Yes, absolutely. We will send out I don't know if we'll send it out or if the recording will just be made available online. Jennifer, do you know if it's just going to be posted on the website or is it going to get sent out? I'll tell you this, if you shoot me an email, I'm happy to send you everything. If it's not it should be readily available, but if you shoot me an email, I'll make sure that you get the slides and the recording if you'd like.
Great, thank you.
So we have a question. Who at MCE should I contact about supporting a field trial of 120 volt plug-in heat pump water heater? That's a great question, Jim Lutz. You should contact Jennifer. You could email Stephen and Stephen can loop you through to the correct person at MCE through us, or you can, yeah, either way. But that's a great idea. Lois says Jennifer would be a good contact. So you can email lsmith@mcecleanenergy.org. And if you don't capture that, if you email Stephen, we'll pass it on through to MCE.
Yep.
I got them all, thanks. Should hear from me later today.
Awesome, thanks, Jim.
Oh, I suppose to give a shout out, this is part of a series, and we will have another one in, I think, 2 months on, I believe, heat pump space heating. So there are going to be total 7 workshops, all kind of in the same vein of electrification, but with different topics. So we'll send out information to the same sort of listserv that you got invited to this from for those as well. Hope you all can attend. Okay, well, it seems like that is the balance of the questions. Unless anybody's got anything else, I think we'll stop the recording. One more call for questions, and then we'll let you get back to the rest of your day. All right. Thanks, everybody. Really appreciate all your time and attention, and hope to see you in a few months. Thanks.